All right, well, good morning, everyone. So today we are going to start talking about active circuits. So far what we've done, we have developed a framework for analyzing circuits. We've looked at nodal analysis and mesh analysis, and what we've done, we've also looked at different various theorems. And we saw that theorems are very important because they allow you to think about it, design in an intuitive fashion, and allow you to design. So they are helpful design tools as well as analysis tools, as you will see. So now, what do we mean by active circuits? We had a definition of active and passive, I think, in the very early lectures. So does anyone remember the definition of an active circuit versus a passive circuit? Yes?
There's like active circuit is one for which at some point the overall work done is less than zero.
So an active circuit essentially is a circuit by which that you can take more. There exists a time, at least one time, where the total energy, the work that it provides, or the energy it provides, is more than what you've ever provided it, ever given it, right? So that's an active circuit. So that's generally an example of an active circuit. Can somebody think of an example of a simple active circuit in our elements, the ones that we have discussed, the ideal elements or idealized elements that we have talked about? Yes. A voltage source, for example, right? Because it can provide power and without having to be provided with power. So of course, at some point, we know that there are more sophisticated physical processes involved, but from an abstraction perspective, that's what it is. So let's start with an active circuit. But so that an ideal voltage source is in general an active circuit. Now we have dependent and independent sources. Now for active, most useful or interesting, useful is not the right word, most interesting active circuits are the ones that have dependent sources, because they can do processing. And this is, so if you have an independent source, it's independent. It does whatever it wants, right? Its result, its output, doesn't depend on anything else that happens in the circuit. It's an independent source, an independent force of the nature independent force of nature within the realm of circuits, right? I mean, it does whatever it wants. Doesn't care what you do. Now, on the other hand, dependent sources would do processing for you. They do something on the circuit, on the signal that's going in through the circuit, right? So that's why I'm saying that they are usually more interesting. So let me start with a very simple example. So let's say we're talking about active circuits. And let's start with a very simple example. Let's say you have a dependent source, a voltage source. A voltage, and we make a special case where it basically depends on another voltage. So we call it a voltage-dependent voltage source. And let's say you have a resistor here. You don't even need this resistor, but let's say you have a resistor. We call it Rn. And let's say there's a voltage across this resistor which we call Vin. So this voltage so these are the two terminals of this resistor. And the voltage across this resistor is called Vin. And this voltage source, this dependent voltage source, let's say its voltage is some constant, A sub V, let's just show it as A for now, times Vin. So what is this? What does this do, if you think about it? So let's think about this as a box. Let's say this is a unit. So let's say if I had a unit like this, so it has 4 leads coming out of it, 2 input terminals, for example, and 2 output terminals like that. What do you think this is? What does it do? Yes?
Transformer, kind of.
A transformer.
Well, like you have an initial voltage going in, and like stepping it on the other side.
Sure, okay. So that's one way to think about it. That's okay. Any other ways to think? An amplifier. Yeah. I think an amplifier would be a better way to think about it. You mentioned transformer, and we'll get to transformers toward the very end of the class. But the transformers and amplifiers are a little bit different fundamentally. Here's the reason. There are 2 things that are different about them. One is that, so since you brought it up, let's talk about this. This is more of an amplifier for 2 reasons. One is that it's what we call unilateral. The way of drawn this thing. So there's a unilateral versus bilateral. These are two ports. We haven't formally talked about them, but let's just briefly mention it because you brought it up. So this is one port where signal can be provided, and this is another port, right? In general, a two-port will have signal flow from any direction to any direction. So if you have signal here, you will have something there. If you have signal here, it will end up here. But if I provide, if there's some signal here coming from the other things that are attached to it, this will be attached to something, right? For it to be useful. We don't know exactly what, let's say, in general. And this will be attached to something. Right? Think outside the box, right? Think outside the whiteboard. But anyway, so this thing is attached to something. So let's say this has some sources and generates some signals and all those things. Would this box, if these two green boxes or green blobs are not attached to each other, if I generate something here, would I see something here the way it's done? Is there any mechanism for this side to what happens, for this side to see what happens on the other side? No. This is what we mean by unilateral. It has one direction. The signal goes from this direction to that, from this side to that side. In this case, from left side to the right side, or from the input to the output. Now, a transformer is different. Again, since you mentioned it, I think we need to. That's okay. We can talk about it. A transformer, generally, a regular standard, like a magnetic transformer or something, is a bilateral device. And a bilateral device can basically, what it means is that the signal from this side ends up on that side, and the signal from this side ends up on that side. So unilateral versus bilateral, also something to learn about. So that's one difference. The other, there's another difference, which is, you could argue, is even more fundamental. Because I could make this bilateral. Actually, how could I make this bilateral? Because we are constructing this thing, right? How could I make it bilateral? I could basically, if I wanted to show the transfer of signal from this side to this side, what do I need to add to this box to capture that behavior? A dependent source on the left side, which depends on the right side, a voltage or current on the right side, exactly. So I can add another source here. And in fact, if I add that and add a resistor here, that would be a general model, one of the general models for a two-port. That's exactly what that two-port. And you can see why, and now that you've constructed it in your head, you will probably never forget it. Right? But anyway, so that's one difference. There's another difference that's a little bit more fundamental. I think, and here's the thing. This circuit, so let's see what it does. Let's go back to this, and let me just grab an eraser. And let's hook it up to something specific. Let's say I put a voltage source here. Thanks to my amazing planning, I have a lot of space to work with here. All right. So the blob will go eventually. Now, so let's say this is some voltage V in. Let's say I drive it with some voltage source V in. And let's say I apply this to a resistor, let's call it RL for load. Now, what is the power that's delivered to RL in terms of V in? What is this voltage? What's the volt? I mean, you know the voltage across the thing, and you have a resistor. What is the power delivered to a resistor if you know its voltage? V squared over R, right? So the power going into this guy, let's call it PL, is V squared over all, which is A V in squared over RL. So it's A squared V in squared over RL. What is the power that's being delivered to R in? This power. And this should be pretty straightforward now, right? What is it? V in squared over R, right? So it's V in squared over R in. So this is P in, the power that goes in. This is the power that's going into the system. That's the power that comes out of this box. Now, what you see here is that, let's just for the sake of argument, let's just, again, assume that R in and RL are equal. Just make a special, so example, for example. So what we're really doing is an example. RL equals Rin, right? And AVA is greater than 1. In that case, what can you say about the P out or PL versus P in? Which one is larger? PL is going to be greater, right? Because these two terms would be equal, and then you have an A that's A squared, which basically when A is greater than 1, it's going to be greater than 1. So what is happening here in terms of energy and power? The energy is not conserved. This is amplifying energy. This is creating more energy. So what an amplifier does within this domain, it can actually amplify power. It has what we call a power gain, too. This is what we call a voltage gain, by the way. That's why initially when I started, I put a subscript of V here. And then this power gain. In this case, the power gain would be equal, if these two are equal, the power gain would be AV squared. Right? But your power gain can be greater than 1. Does that mean that we've violated the conservation of energy? Well, hopefully not. But so where is that coming from? What's happening? Yes?
Presumably the voltage sources are providing some sort of energy?
Yes, but where is that coming from? Right? So that's a good, your answer is correct. So the response was, presumably the voltage sources provide some energy, which is correct. Yes, the energy is coming from the voltage source, but where is that coming from, really? And at some point, so what that tells you is that you can't make these things in isolation really like that. Generally what happens is that there are things that are not shown here, which means that there's a source of energy here, for example. This has a power supply. This box has a power supply, 1 or 2 or multiple. And that's where the energy comes in from. That's where the energy comes from. Your energy comes from these sources, these power supplies, for example, right? So that's another difference. Now, going back to your question, the reason I brought this up is that going back to your transformer comment, transformers do not conserve, do not generate energy, right? They actually have loss generally. A non-ideal transformer, a realistic transformer, cannot produce more power at the output than at its input, because it also is warming up a little bit, right? And what that means is that it can't have power gain. The way it happens, again, I'm jumping ahead a little bit, but that's okay. The way it happens is that, yes, you can get an increase in voltage. You can increase the voltage, but you're paying with that, for that with something else, which is the current, right? So the product cannot increase, which is the power, right? The product of the voltage and current. So yes, you can jack up the voltage, but then what happens is the current will go down, at least by the same factor. And if you have loss in the transformer, it will more than that factor. So yeah, that's why I kind of like got into it. But it's a good comment, so I wanted to make that distinction. So having said all of these things, this is an amplifier, right? So this is a very simple amplifier. This is an example of a voltage amplifier. And as I said, in reality, these things would require certain power supplies and all those things. So that's fine. But now, in reality, one kind of this amplifier, which is extremely common and extremely useful, if you know how to use it, is so-called operational amplifier. Or op-amp for short. So you will hear op-amps. And what an op-amp really is something very similar to this. An op-amp, and a symbol is like this sideways triangle shown like this, which has two input terminals, a positive terminal and a negative terminal. And inside the model for it, I mean, how it's built is a completely different thing. That's one of the things that we'll cover in the later courses. We'll build these things and design them and see how it's actually made. It's a whole process. But the way it will look to us is that it looks like a voltage source, in general with some sort of a source resistance, let's say R out. And these two input terminals also have an R in, an input resistance. There is some voltage gain, AV, times this voltage. Let's call it V1 or V in. Makes more sense that way. So this terminal is called the output or V out. This generates V out. And this sometimes is shown as V in plus and V in minus. And what this really is that essentially what it says is that another way to write this, and I'm running out of space, is that this is equal to AV, V in plus minus V in minus. So it takes the difference of these two voltages and multiplies it by a gain, by voltage gain, by some constant scalar number. Well, some scalar number, ideally constant, practically not. And then that generates that voltage here, and depending on what kind of load resistance you connect to it, you will have a resistive divider, essentially, between what that load is and this R out. That would determine your V out. Right? So now, in reality, an op-amp must have at least 2 more terminals. If you go and buy an op-amp from, like, pick one from the stock room or something like that, or buy online, you will see that it does have more than 3 terminals. So the one other definitely necessary terminal that you have is a power supply. Sometimes we show it as VC plus VCC and negative VCC. Sometimes they're referenced to different voltages. You can reference them to different voltages. So the idea here is that one way to think about this is that you can think about this being 2 batteries of value VCC negative VCC here, and then there's a ground, so this could be the reference potential, so this is VCC, this is VCC, so this produces a negative voltage, negative VCC here, and a positive VCC here. And that's where all the energy for this comes from. When you're amplifying power, you're essentially taking, again, the power from this DC battery and convert it to what we call the signal, or AC. So it's a means of converting the power from DC to AC, or whatever this input signal is. So you put some sort of a voltage here between these things. Maybe you hook it up to a microphone, and then that microphone that, for example, I'm wearing, this signal is very weak because it's generated really by what? By vibrations of a membrane that's sitting very close to something else, either magnetically picked up or electrically picked up. A capacitance changes or an inductance changes, and that is a tiny, tiny voltage that's going through this wire to this device, and then this device basically takes that and amplifies it. So when it comes out, it's hopefully a good replica of that, but just larger. And it's amplified. And then, of course, a whole bunch of other things that happen inside this box for now. We won't talk about that. Okay? But the square? Yeah. Oh, no, the squares are just, these are wires. Okay. So, sorry, maybe I should have drawn them with a different color. So this is basically 2 batteries, right? And this is connected to this terminal, and this is connected to this terminal.
Oh, those are the terminals.
The other terminals, yes. Let me just maybe put them like this. The terminals of, so this is basically the power or power supply terminals of the op-amp. And they are provided with some power through the batteries, for example, or some power supply, something. Right? So this picture really, the part that matters, so from now on, we won't show this part, right? I won't show the part, let me just maybe, you know what, I'm going to do this to differentiate it. What I should have done to begin with. And I won't show the orange stuff because a lot of times we won't show it. It's implicit when we draw it. So it's like when we draw this box, when we don't show those a lot of times. But I wanted to show it, let you know that it really is there. If you buy an op-amp and hook up these 3 terminals, it won't do anything. It won't have any gain. It would have a nice loss, actually, because it shouldn't. There's no preferred point in time, which means that the energy is conserved. Okay, so that's for that. But now, when you look at an op-amp, well, maybe I should say this here before I get down. So Okay, so this is some model for this. So what do you expect these resistors and gains and things of that sort to be in an ideal op-amp? When I say ideal, if you want to idealize it to the point that you can, what do you expect the AV, voltage gain, R in, R out to be? So let's say AV, let me just get rid of this. Voltage gain, R in, R out, ideal and practical. So ideally, what do you expect the R in and R out to be? And maybe even VCCs. So what is the gain of the ideal amplifier, ideal op-amp? This is, you want it to be as high a gain as possible, in fact. Yes? Infinity, right? And you may think, say, okay, what is the use of something with a gain of infinity? I can't use it on anything, right? Because if I apply something with the smallest amplitude, it would basically grow to be incredibly large if it's really mathematical infinity. So what's the use of that? And you will see that the use of this thing is actually that we rarely, very rarely and almost never use the op-amp in this configuration, what we call an open loop configuration. We apply feedback to it. And I'll show you an example of that. We'll talk about feedback later on in the future courses extensively. In fact, it's one of the core concepts of electrical engineering and understanding what happens in the presence of feedback and all those things. But right now, that's the reason. And you will see that when you have a negative feedback system, which is basically what a lot of these things are generally used in, the higher this gain is, the better your behavior is, the more predictable your behavior becomes. And we'll see that in like 5 minutes. So that one I'm not going to pass the buck to someone else. I'm going to take care of that in 5 minutes. But anyway, so take my word for that, on that, and then I'll try to convince you within the next 10, 15 minutes. So what is it practically? Practically, obviously, it can't be infinity, right? So practically, it can be anywhere between 10 to the 6 to 10 to the 8. So it's still pretty large, actually, the gain of an op-amp. I mean, there may be specialized op-amps that will be outside this range, maybe on the lower end or even higher end. But a vanilla op-amp is going to be in that range. Yes?
What is that limited by, like the input impedance of the op-amp?
What is it limited? What is the gain limited by?
Yeah.
Okay, so let me ask you, so the question is, what is the gain limited by? Your question is, why can't it be higher? So it can be. If my objective is to increase the gain. Let me ask you a question. Let me throw it back at you, right? And so in the sense that if you came to me and said, well, how can I increase this gain? And I would ask you, how can you increase this gain? Can you think of a way to make the gain larger? Yes, stack them. I mean, stack is probably not the right terminology. Cascade them or put them in series. Stack means put them on top of each other. Stack, because that also is used. That terminology is also used for something else. So we want to save it for that. You want to cascade them or put them in series. Because once you put two of them back to back, what will your gain be if one of them is 10 to the 6? 10 to the 12, right? Because they multiply. So you can easily increase it. So you can say, why do you limit it to 10 to the 8? That goes back to something else. In the sense that if you were making open loop op-amps that you were not planning to use in feedback, you can make it as arbitrarily large. You will find out that it's pretty useless because if you have something that has such a high gain, it will be extremely sensitive to small noise and fluctuations that will happen at the input. And some of them are intrinsic to the circuit. But let's say you can get around those somehow. But if you do that, still you have another problem. This is limited by trying to maintain the stability of op-amp. And again, that's not something that we have talked about. We'll talk a little bit about stability later on in more general terms. But then that's analyzed when you get into an actual op-amp design class, when you see that you really do not want to have, sometimes you basically, to get more gain, you need to cascade more stages. And when you cascade more stages, each stage has its own dynamics. And when you use those in feedback, it can produce instability that can show up as the system, instead of amplifying, become an oscillator. So those kind of things can happen.
Is that like a concern that we should have, like, if we just like cascade like 4 or 5
If you cascade 4 or 5 of them open loop.
What do you mean by open?
Open loop meaning that there's no feedback from the output to the input. I will show that in like probably 5-10 minutes. Yeah, but so I'll show you what, because we haven't applied feedback, and you say, what is feedback? And you know, this is an abstract concept right now, but I'll show it to you. So why don't you bring it back at the end of this, this lecture, so if I didn't cover what your question was. Okay, any other questions? All right, so that's good. So that's the typical range analysis. How about Rin? If this is used as a voltage amplifier, what do you want the Rin the input to look like? What is the input really? Is it if you're trying to measure a voltage, what is the ideal device that measures a voltage? A voltmeter, an ideal voltmeter. And what is the impedance of an ideal voltmeter? Infinity, right? So ideally you want Rin to be infinity too. Practically it isn't. Practically it can be anywhere between 10 to the 5 to 10 to the 13 ohms. So you can actually make it pretty large without a significant hit on the performance. So this is not one of those things that has this like hard trade-off. There are like more secondary trade-offs involved in how large you make it. And sometimes at some point it's useless to do that. You will see why it's useless to do that because of another thing that will happen when you apply feedback to it. So this input impedance being extremely large is not particularly useful unless you are using it in special applications. Now, how about R out? What do you want R out to be? You think about the output. Do you want the output to look like what? If it's a voltage source, if it's a voltage amplifier, it has to look like a voltage source, right? For it to look like an ideal voltage source, what does R out need to be? 0, right? So ideally you want it to be 0. Practically, for a typical op amp, it can be 10 to 100 ohms. There are specialized power op amps that have much lower output impedance, or output resistance, more accurately in this case. And now the VCC of the op amp, the voltage supply, excuse me. So it can be anywhere between like, I don't know, practically it can be anywhere between 1.5 volts to 30 volts. Again, these are different op amps. So ideally, what do you want it to be? Well, from the energy consumption perspective, yes. But remember, if the VCC is 0, then the current is infinity. If what you said would be useful if you didn't have conservation of energy. If there's conservation of energy, if you make the supply voltage 0, then it means that to generate power, it needs to draw infinite current, which is not a good thing. So actually you want it to be, you say, why does it matter? Well, there's something else that we haven't talked about. So if you look at the V in versus V out, V in meaning V in plus minus V in minus, right, of the op amp. Ideally, so what do you expect it to look like? So this is a pretty high gain device, so it has a pretty steep curve. It's a curve. You want it to be ideally linear. It isn't, but let's just assume it's linear. And it's a lot steeper than this. Of course, it depends on the scale on which I plot this. If I were to plot this on an equal scale, you wouldn't see it. It would be just like a line. You would see a vertical line. Because it's a line with a slope of like 10 to the 6 to 10 to the 8. Right? So you had to draw this on a very different scale than this. This has to be on microvolts. This has to be on volts, for example, for you to start seeing this. But anyway, so let's say you do that. But then how far does it go in practice? Can it go above VCC? Well, yes, it can, but you have to do something special again. You can design a special op amp, but practical op amps usually do not exceed VCC or negative VCC. And sometimes, actually, they usually don't even get there. There's a little bit of they stop before that. So there's this, what we call the saturation that happens in practical op amp. So ideally, what you want the VCC to be? Well, you want the VCC to allow you to have a large range. So ideally, from the range perspective, you want it to be as large as possible. So I would put an infinity with some sort of a kind of like a question mark or something like that. So you know what I mean. Because then there are other implications if you have something that's infinity and then what happens to voltages and breakdowns and things. So you want it to be large enough. So how about this? How about we replace this and say large enough for the signals. So it's really two different things I'm talking about here, right? And I conflated them. And that's why the problem arose. Because, yes, if the supply voltage itself is concerned, it doesn't matter what it is, or it can be small. What I'm really asking you is this basically a range. And I want that to be as large as possible. So the problem really arose from the fact that I tried to put two things into one line, two separate concepts. Yes?
Why do you want the range to be as large as possible?
Well, because it allows you to kind of like, because think about it this way. If I put a signal in, if it exceeds the range, so let's say if the range is here and there, you start clipping it, right? So my voice will not sound as good. If I start yelling now, we may get into that range. Or if we increase the gain on that camera or gain on this, you can't hear it, but people who will be listening to the video or watching the video would be hearing. Just like it's distortion. It sounds bad. Any other questions? No? All right. So that's basically all about like the ideal op-amp and differences of with the ideal. So now let's go back to this thing that we talked about. How do you use an op-amp? How do you use if you had an idealized amplifier? And let's start with really the most idealized case, and then we can talk about a little bit less idealized. Let's assume R in is infinity, and R out is 0. Let's keep the most essential part of the op-amp, which is only that dependent source. If infinities and zeros bother you, you can say, OK, R in is very large. So let's take this op-amp and make our first real amplifier with that. So this is where feedback comes into play. We said the op-amp, the ideal op-amp, has a gain that approaches infinity. When we say approaches infinity, it means that for all intents and purposes is large enough. So if I apply, I need to somehow control this. So what I do, I apply a resistor here. Let's call this R2. Between the output and the negative terminal. And let's say I connect this to ground, a reference potential, right? So this is my reference potential, this positive terminal. And this negative terminal is connected to the output. What will happen if I just do this? Think about it this way. One way to think about it. So let's say, you remember this is an amplifier, right? So it has huge gain. So if this node goes up a little bit, the voltage of this node goes up a little bit, increases, right? What will happen to what would the op-amp try to do to the output? Increase or decrease? Look at this. It will go down, right? I flipped it. I made it upside down. Right? So and it's common to flip these the way you prefer. So what happens to the output? What does it do to the output? Starts yanking it down, right? So wait a second. The input is going up a little bit. Oh, so this voltage is becoming negative, so I have to AV times that, a large voltage. So this starts going down, which would do what? Which would counteract this behavior, right? If this were to go down, this would push it up. So that's actually kind of, it can, if for example, if this happened instantaneously, if there was no lag, if there was no delay or time shift, this would completely force this to be at some fixed value, right? It's a stabilizing mechanism, right? It's this thing I'm trying to go. It's going this way, I'm fixing it the other way. I'm pushing it the other way, right? And you know, by the way, why it becomes easier, this like inverted pendulum or whatever you want to call it, becomes easier as you make this longer? Think about it. Have you ever thought? It's a lot easier to do it with the longer one than the shorter one. Right? Why? My moment of inertia, what about it? What does it do? Yes?
It increases your moment of inertia, so you need to actually apply more. There needs to be more torque.
Yeah, I need to apply more torque. Well, yes, but it also does something in terms of, I'm a human being. I'm not an ideal response system. So, okay, so let's see here more. Then.
The fact that it's larger means that whenever like the
Right.
so you can detect your one.
Detect it, correct. But then, okay, so carry on. We are getting closer.
I think the moment of energy goes up by r squared, but the torque only goes up by r, so
Response time, yes. So he says, okay, so the response time, exactly, right? So it takes less time. I mean, I have more time, essentially. So its response, initially it's slower, so it gives me more time. So here, this op amp, at least the ideal op amp, is infinitely fast. So the slightest variations it immediately fixes. Now, a real op amp is not infinitely fast. It has bandwidth. It has dynamics, and these are the things that we talk about as we go through this course and other courses. So what happens is that, as a result, there's limitation on stability. And what happens is that if you apply the wrong kind of feedback or too much of it, then you can be in a situation that this can happen. Again, very qualitatively. This can go up. It says, oh, okay, what's happening? Let me see, think a little bit about it. Oh, okay, now I have to go down. There's some time that's passing. So this voltage has gone up a little bit. This says, oh, okay, let me pull it down. And it says, okay, it pulls it down. And this goes down now. So this goes up, and then this goes down. So it brought back down. It overdoes it because it doesn't see that it has already been fixed. So it overshoots. It goes beyond. And then says, oh, wait a second, I'm going too far down. I have to fix it more. I go up. And say, oh, that's too much. I'm going down. And then, oh, that's way too much. And then, that's instability. And you will see, actually, we'll talk about the kind of systems that generate this. This is a growing sinus, it's an exponentially growing sinusoid. That's one of the things that can happen if your system is unstable. And we'll talk about that in this class later on. But that's what happens, right? Because of that lag. But if there was no delay, immediately fixes and nothing happens. So anyway, so let's assume that we are in that mode. So, oh, great. This is a semi-permanent marker, I guess. I guess everything is semi-permanent. There's nothing permanent in this world anyway. Oh, yeah, see that? You get philosophy for free in this class. Say again?
Do we get to count this as a poem?
Yes, sure, yes. Yes, you can do it. It should be /philosophy. All right, okay. So anyway, going back to this. So let's see okay, so that's fine. This is qualitative. What qualitative is important. So is quantitative. So you need to be able to understand. Because if you just do quantitative, you don't know what you're doing. You're just dealing with a bunch of notations. If you're just doing qualitative, you would be like one of those people who have an idea but can never execute. Right? So you need both. Okay, so let's go back to this to see what happens. Now, quantitatively, what happens? So there are different ways to do this. Let's just do it first the brute force way. So this is AV, or A, times V in. And V in this case, so this voltage is 0, because this is ground. Right? So this voltage, let's call it whatever, V1. So this is going to be negative A times V1. Because of the polarity. It's a different, this minus that. And gets amplified by that. So this voltage that this generates, so basically it's going to be negative A times V1. But now, if the input resistance is truly infinity or very large, what is this current? That current is 0, right? So if that current is 0, what is this going to do? So we have, these two, so what is the voltage across this resistor if its current is 0? 0. So these two voltages have to be equal, right? So it says V1 equals negative AV1. What is the solution to this equation? There's only one. What's the solution? No. Let me just write it slightly differently. Maybe it helps you. Let's divide by 1 plus A. Right? If I say 1 times something equals 2 times something, what is the something? 0, right? Okay, so it says this voltage is 0. It forces this voltage to be 0. Not positive, not negative. It basically forces it to be exactly dead in the middle if you do that. Now, let me ask you a question. What if I had a voltage source here that had a different value? Let's say I put a battery here of 1 volt. What would change in this analysis? So let's see. A times V in. What is V in now? V in is 1 minus V1, right? So now this becomes A times 1 minus V1. Then this becomes A times, okay, A times 1 minus V1, right? And then if I solve for this, if I take this one and bring it to the other side, I'm left with A on this side. I'm going to be left with A over A plus 1. That would be my output voltage times 1 volt, really. All right? So what is that? No, wait a second. Just we are not done yet. But this is an ideal op amp. What does that mean for A? A is very large. If A is very large, what is this? What is 1 million divided by 1 million and 1? 1. Thank you. This is engineering, right? It's not point. Well, it is 0.999. It's not, but anyway, okay. But so for all intents and purposes, it's basically 1 volt. The larger A is, now, and if you take the limit of A going to infinity, then this is going to be identically 1. Yes.
What is the A times 1 minus V1 originally? What is that?
Where did that come from?
Yeah.
Okay. So remember, what is this? This voltage is A times V in. What was V in? V in was this voltage minus that voltage, right? Right? Remember the expression V in plus minus V in minus up there? So V in plus is 1 volt. V in minus is V1. Right? So now, if you have 1 volt, this circuit forces this node and, of course, this node to be in this configuration to be exactly at what? At 1 volt. So what is it doing, really? If A is large, it doesn't matter. And even if you had a resistor, if I have actually put the resistor here and do the calculations again, you will see that if A is large, and if you're in negative feedback configuration, the way to check for negative feedback configuration is to see if a node goes up, what does this do to bring it back up? So if it goes up, you will see this is going down, which means that it's pushing this node back down. And if that node goes down, it means that through this resistor, it will be pushed back up. So it counteracts its movements. So that's called negative feedback. And you can imagine positive feedback would be what? If it did the opposite, if it went up a little bit, then it pushes it up further. And that can also definitely lead to instability. How? So basically, let's say it goes up a little bit, say, well, okay, push it up further, further, further. So you will have an exponential growth. And you will see when you have unstable circuits, you will see these kind of behaviors. We'll derive these things later. But anyway, so going back to this thing, you will see that if A is large, if you just assume that A goes to infinity, and you have negative feedback, then this kind of system forces something to be equal to something else, which also makes sense. What two things are forced to be equal? Make an observation, makes an extrapolation from these two observations that you had. Anyone? Thoughts? Yeah. The two inputs, right? The two input terminals, right? So the voltages of the two, so you can see it forces them to be equal. Why? Think about it. If you have negative feedback, it generally means that you have stable, constant, finite voltages. To have a finite voltage here, now this is the part I want everyone to pay attention to. Wake up for a second. Just listen to this one. This is important. If this voltage is finite, while this gain is infinity, what does that imply for Vn? An infinity times something gives you finite. What is that something? 0. This is what we call the principle of asymptotic equality. So it means that asymptotically, these two are equal. Equality. It's a very powerful principle. I mean, we will use it a little bit in this class, but there are other places where you can actually use this extensively. So if you have negative feedback and you have very large gain, these two are forced to be equal. And if you have that, then you can analyze a lot of things simply. So let's look at certain circuits and analyze them. So for example, let's take this circuit. So let's call this V in, V out, R1, R2. And this is a ground for now. Okay? So if we know that this is let's say this is an ideal op amp. The first thing we need to check is the sign of our feedback. How do we check the sign of our feedback? We say this goes up. What happens here? Somebody? If this note goes up, this voltage goes up, what happens to this voltage? It pushes it down, which basically through here will push this voltage back down. Which means that this is negative feedback, right? I could have made it positive if I had done it this way, if I had connected it the wrong way. Not the wrong, I mean this a different way. Say. If I had connected it this way, this going up would cause this to go up, and this would go up, so that's a positive feedback. So for asymptotic equality to apply, you have to have negative feedback. That's an important condition. Don't forget that. Only for negative feedback. Only for negative feedback. Okay. So now I said I have large gain and I have negative feedback. What does asymptotic equality tell me about this voltage? What can you say the feedback loop does? And listen to this sentence carefully. What does the feedback loop do to this voltage? What does it force it to be? It forces it. What forces it to do two things to be equal? What two things? These two voltages, right? So these two voltages are forced to be equal, and as a result, this voltage would be exactly equal to that. In this case, this voltage is 0. So what can you say about this voltage? Now, it's not equivalent to, it's not saying that this is connected shorted to ground with a short. It's the feedback loop that forces this to be 0. It adjusts its voltages to the point that these two become equal, because that's the only way it can maintain a finite output with infinity gain. Right? So I want you to make this distinction in your mind. Now, okay, so if that voltage is 0, let's find out what's the relationship between V in and V out. It's very simple. How do we do that? Well, what is this current in terms of V in and R1? V in over R1, right? What is this current in terms of V out and R2? V out over R1? No, well, we'll get to that. No, we're trying to. That's another equation. You're right. These two equations are equal. These two currents are equal, but we'll get that. Before we get to that, if I look at these two, I know this voltage is 0, this voltage is V out, and this resistor is R2. What is that? Say again? V out over R2 with a little difference. Negative V out over R2, right? Because this current is drawn point this way. Does that make sense? Now, you said these two currents are equal. Why are they equal? How about this current? Why is it 0?
Because we said that's infinite.
Okay, what if the input impedance is not infinity? Let's say you're dealing with an ideal, not ideal in the sense that the op amp has an R in. Would that current be non-zero? Yes.
Yeah, it'd be non-zero, but if R1 and R2 are much smaller, then
Will it be non-zero really? Think about the voltage across this resistor. What is the voltage across that resistor? 0. So what is the voltage across, current through that Rin, independent of what Rin is? 0. So this current is always 0, even if you have a finite Rin. When you have large gain. See, do you remember? See, this is the magic of that large gain, actually. And you don't even care what it is as long as it's large. That's the beauty of it. When you design an op-amp, essentially, you get to a point, say, I don't know what the gain is going to be. It's going to be roughly in this range, but I can say it's larger than this number, so I'm good enough. Got a question, or you're good?
Yeah, so if the gain is significantly large, the two voltages are going to stay the same, like, regardless of the impedance between the two?
Right. So the question is that if the gain is sufficiently large, these voltages are going to remain the same irrespective of this voltage, and that's correct. Yeah, of this value of this resistance. These two voltages are going to remain. Yeah, because if you force these two voltages to be very similar, even if this is not very incredibly large, the voltage across it is 0 or very small, so it's not going to draw a lot of current. If you make this 0 ohms, then it's going to be interesting because, it depends. The question is that is this 0 more of a 0 or that infinity more of an infinity? Okay, all right. It's the irresistible force hitting the immovable object kind of situation. You see, humanity. So you can pass it as a hum too. Okay. So all right. So fine. So this current is 0. So what can we say? These two currents have to be equal. So I can write them in terms of those two voltages. So V in equals R1 equals negative V out over R2. Therefore, V out over V in, which is really the gain of this new amplifier, the ratio of the output voltage to the input voltage of this new thing that we've built with the resistors and the op-amp, is going to be negative R2 over R1. This is called a basic inverting amplifier, op-amp inverting amplifier. Why it's called inverting? Because of this minus sign. Because if you have a waveform at the input that looks like, looks like this, at the output you will get something that looks like that. It inverts it, flips it upside down. Okay, any questions? All right. No. Now, so you can see even that resistor doesn't matter. You can redo this calculation with the resistor. And I think one of your homework problems, you will do that. Do your KVL, KCL, and write this and show as A increases what happens to this voltage. You actually will monitor this voltage and see what happens for different values, so you get a better sense of what this really does. So that's an inverting amplifier. Fine. Now, if I wanted to make non-inverting amplifier, can you think of a way? I wanted to make something that has a gain that's controlled, by the way, like this. Now, you may say, wait a second. What was before we get to the non-inverting amplifier, let's talk a little bit about this. You may say, wait a second, why are you doing this? It seems that you just went out of your way, you made some amplifier with a tremendous amount of gain, a lot of gain, and then you destroyed that gain, and then you made something that has, let's say, if you wanted a gain of 10, you make this 10 to 1, this can be 10 kilo ohms, this can be 1 kilo ohm, and then you will get a gain of 10. Why didn't you make an amplifier with a gain of 10 to begin with, instead of like doing this complicated thing? Can someone think for good reason for not doing it this way, or doing it this way as opposed to the other way? Any thoughts? Why you may have this is a good way of doing it, by the way. Yes.
If you just made the amp with like a gain of 10, then you'd run into issues with like non-ideal behavior because like 10 is not.
So you say you run into issues if you were to make it out of a gain of 10, you would run into non-ideal behavior. And that's correct because it's very general. What do you mean by non-ideal behavior?
So like you can't really make the statement that like Vn equals 0.
Well, but there are lots of different ways to make an amplifier, right? And some of them may be good for other applications. If you're making very high frequency things, you won't do it this way because this is not going to be super fast. But it's super something. Say again? You have to speak up.
So if you made an amplifier with a specific gain to start with, then you would only
Okay, so that's a good point. So she said if you started with something that had a specific gain to begin with, you can only use it for that. This one has versatility, flexibility, because you can actually change these resistors and get different gains. That is true. That's a correct statement. So with one kind of thing that you instead of stocking the stock room with like 10,000 different kind of amplifiers, a gain of 2 amplifier, gain of 3, gain of 4, gain of 5, gain of 6, gain of 10, gain of 12. So you can just basically have one that has like you can get everything out of, and you stock it with few resistors, which are a lot cheaper. So you can control the resistor, you can change it. There's something even more fundamental to that. See, controlling the gain of an active device, because it's coming from a pretty complex solid-state device that has a lot of interesting dependencies on temperatures and other parameters and all those things. Controlling it and getting something fixed and controllable is hard. It's hard to make an amplifier. It's not, well, it's doable, but it's challenging to make an amplifier, which has a very large gain and it's very well controlled. You can say, my gain is exactly 100,000. You know, when you make these op amps that have a gain of like 1 million, yes, it's 1 million, you breathe on it, it's 900,000. You look at it the wrong way, it's just going to be 950. Right? So it's basically very, very sensitive. Now, when you do this, you desensitize it to all of those things that are inside. You've actually, essentially, we have lumped everything, all the complexities in this thing. There are different levels of complexity, and this is really very, very simplistic, simplified. But all of those complexities are irrelevant in this case, because as long as A is large, they disappear. So all you're dependent on is not even a resistor. It's even better than that. It's the ratio of 2 resistors. So if, for example, they have temperature dependencies, if you pick them of the same kind and keep them close to each other, if the temperature goes up, they will increase by same ratios, but each one of them increases by some factor, but the ratio does not increase or decrease. So it desensitizes your system. Does it make sense? So there are lots of good reasons for doing it this way. Things should make sense, right? When you see people doing something and you say, why are they doing it? Why aren't they doing it the other way? You have to ask that question and you have to answer it in your head before you can move forward. Otherwise, you haven't understood it well. Or sometimes, from time to time, when, every so often, if you actually keep doing that, you run across things and say, wait a second, why are they doing it that way? And see, when you look at it, and eventually you find out it was for a historical reason when there was another problem, and now there isn't. So you can say, oh, maybe I can do it this way. And that's basically how you come up with new ideas, how new ideas are created, and you come up with new things. That's how new things are created. Anyway, so that was an inverting amplifier. How about making a non-inverting amplifier? So let's say I have my op amp, and I want to make a non-inverting amplifier. So say again? Put 2 of them together. That actually kind of works, yeah. So you can take 2 of them. When you say put 2 together, again, I want you to start practicing a more precise language. Put 2 of them in cascade 2 of them, or back to back, or in series. Right. So you say put 2 of them together. Minus times minus is plus. That works. That works, but you use 2 op amps and 4 resistors that way. So what if you had only 1 op amp to use? That's a reasonable thing to ask, by the way, just because then you will dissipate twice as much power. And power is important because your battery will not last forever. So if I wanted to make it with 1 op amp, how would you do that? So if you use that inverting amplifier as a template for this, think about it. Yes?
Just do the same thing but on the positive.
So you mean that I basically do this?
The goal is to make a non-inverting.
Non-inverting amplifier, yes. So you say do this, right? Okay, so that's a good question, right? I mean, she says she's right. She says you have positive feedback. This goes up, this goes up, this goes up more, this goes up more, till you hit those VCC lines, and then you have something that nicely produces a large positive or negative voltage and doesn't amplify anything. So you can't make the, I mean, if you go positive feedback, it's a whole different ball game. It's also useful for other things. It was actually used before negative feedback, but that's beside the point in this class right now. But so that's not going to amplify. You can do other things, but not amplify. So the feedback needs to be negative. So there are 2 things. The feedback needs to be negative, and the input needs to be applied to the positive terminal. Right? because you want it to be non-inverting. So for the feedback to be negative, this is the way feedback is negative, right? So now, remember superposition? Remember when I put a 1 volt voltage here, what happened? So what if I get my, say, okay, you know, I had a source here. This was a voltage source, but now I cannot ignore that. I make it ground. I null it. This still maintains the negative feedback, right? But where do I put my voltage, my input now? Here, right, yeah. So I can apply, I can think about it as a voltage source, or I can just write it as V in, which by substitution theorem is the same thing. And then this is V out. And let's quickly do this one too, based on, so let's say the gain is very large, use the asymptotic equality principle. It says that these two have to be equal, since now the feedback is negative, right? These two voltages have to be equal. So what does that tell you about this voltage? This voltage will be what? V in, exactly. Thank you. V in. And we argued that since these two are equal, the current through here is 0. So this current has to be the same as that current. Right? What is this current in terms of V in? V in over R1. And what is this current in terms of V out? Or and V in? V out minus V in divided by R2, exactly. So I have this equation, I move this term to this side, so I get V in times 1 over R1 plus 1 over R2 equals V out over R2. I multiply both sides by R2 and divide by V in, so I get V out over V in of 1 plus R2 over R1. So the gain of this thing is a little bit different. So if I wanted to get a gain of 10, I would need a 9 to 1 ratio. So I make this 9 kilo ohm, 1 kilo ohm, because there's a 1 plus that. Slightly different, but it's a non-inverting amplifier. In fact, you can use these kind of things a little bit, take them a little bit further. You can use it for as a summation. So remember, there's something interesting that happens at this node. This is one of the fundamental concepts of electrical engineering, and even a lot of electrical engineers won't articulate it this way, but you will be from now on. This thing here, this node is very powerful. We call it a summing node. Because what happens is that it's a place, it's like a bank. Everyone pours the currents in there, and it just makes sure that they are all equally added, and it doesn't tax it at all, or very little, because of this feedback, because of the A. So it's a really kind of perfect bank, or the perfect government, right? But, so it doesn't take anything away, it doesn't add anything, right? But it allows you to make the perfect, or perhaps the most accurate analogy is the perfect market, the perfect financial market. Right? So it just becomes a mechanism for exchanging very rapidly and effectively. Okay, so what's happening here is a summation, right? Summation of these two currents. I mean, it's an algebraic summation. So it doesn't have to be limited to 2, right? You can do it with more than 2, or here, right? So what if I add another branch here? Let's say, so let's call this V1. And let's call this V2. And let's call this, I don't know, big bad naming convention, just, let's call it VA and VB. And this is called this RA and RB. Okay? So now what's going to happen? The sum of these 3 currents has to be 0, right? Because of negative feedback, this voltage is still 0. What is this first current? Let's use a different color. What is that first current? VA over RA. And then what is the second current? VB over RB. Right? These two have to be equal to negative V out over R2. So if I look at V out in terms of these things, V out is going to be negative R2 over RA times VA minus negative R2 over RB VB. So I can form a weighted sum with amplification by adjusting RA and RB. If I make RA and RB equal, then it becomes a summer and addition. Right? You can add two signals, two voltages to each other. You can add 5 voltages to each other by adding 5 of these branches. You can subtract them by applying them in opposite polarity. You can subtract things by putting them on the negative terminal. You can combine these elements. Now you can think about design. So you have 2 or 3 things that do things and you understand them well, you can put them together with different ways. And superposition is the useful thing because it allows you to put them together without destroying the overall system. Yes?
So it's only in the case where the negative feedback forces the V to be 0, right, at that terminal?
VA, you mean?
Yeah,
V0. Yeah.
the total voltage.
Right.
So in cases where you maybe have 1 volt of difference, that wouldn't be the case.
Sure. So the question is that this is only valid if this voltage is forced to 0 if this is grounded. Yeah. So you get a difference. You get that. So that's basically where you get your subtraction, because you get the difference of this voltage and that voltage. So you can actually, if you make this 1 volt, you get this volt, whatever this is, minus 1 volt. So you can actually write expressions that have both positive and negative terms.
So it's just shifted by 1.
Correct. It's a shift, exactly as you said. It's a shift that you can take advantage of. You can actually use for something. So this is, again, there's a whole lot of different things on this front. And I want to say one more thing before we take a quick break. Now, active circuits can do also kind of funny things. So let me show you an example of something funny they do. So think about this circuit. So let's say you have a voltage source. Let's just, okay. V1. And let's say you put a resistor here, R1. So now this is basically using dependent sources. So let's say the voltage across this dependent source, let's call this V1 or Vx, whatever. And then make this mu times Vx. Okay? So the question is, what is Vx? So if you were to solve this problem, so this is an example to show you what's something funny, some interesting things that can happen. So what does it say? If you write KVL, we know V1, right? Let me just make sure that I got the, this doesn't matter. V1 minus mu Vx is the voltage across this guy, or the other way around actually. Mu Vx minus V1 is going to be Vx, right? This voltage minus that voltage is this voltage. This minus that is this. So I can solve for V1 times mu minus 1 Vx is equal to, so V1 is equal to mu minus 1 times Vx, and therefore Vx is going to be V1 over mu minus 1. Nothing really that exciting so far, unless you set mu to 1. Right? What's going to happen to Vx? It's going to explode, right? It's going to go to infinity. So if mu goes to 1, Vx goes to infinity. And what does that mean? That really is interesting because, so this is a way where you can, another way where you can actually make the determinant of the Y matrix to go to 0. And you will see, or you have seen, you're about to see an example of that in your problem sets. When with the right setting one of the parameters to one of the values, you can actually make it go crazy. So you can actually make the determinant singular. What it means is that essentially exploding. It doesn't have a finite answer. Now, what is really happening is kind of simple if you think about it. If you think about this combination of these two, if we define this as Vx, the substitution theorem tells me that I can replace this with what? With an ideal voltage source of value Vx, exactly, right? So I can put a Vx here. So this is V1. And then have this guy that's mu Vx. Now we set mu to 1, so this is going to be Vx. So these two together, what are they? The series combination of two voltage sources with the same magnitude and opposite polarity is 0, a voltage source with value of 0. So this is, so this thing is a voltage source with a value of 0, which is what? This is a voltage source with a value of 0, right? A short circuit, right? So you're short circuiting a voltage supply. You remember? It's this, we said that this is equivalent to saying this. And if V1 is non-zero, then this is not going to be happy. If you say V1 is like, I don't know, 3 volts, then it's going to be equivalent to saying 3 equals 1. 3 equals 0, sorry. 3 equals 0. So yes, I mean, you created a mathematical contradiction, and therefore it shows up. This kind of things also show up in Y matrix determinant becoming singular. So you got to be careful with these things. They can actually be useful, too. You remember that thing that I showed to you earlier? This is slightly different, but you remember it goes a little bit up, and then before it can react, it goes down, it goes up and down, up and down. So if you want to make an oscillator, that's probably the best way to do it. I mean, that's what you do. You create circuits that intentionally and controllably do that. All right, so let's take a quick break, and then we'll continue afterwards.